Hello everyone, welcome to this very first lecture on structural dynamics. In today's class, I would be just giving you a brief introduction about this course, and that will include the concepts that you would be learning as part of this course. Then I will give you a general idea of what is a static loading and what is a dynamic loading, and what are the key differences between dynamic and static loading in terms of their effects on a structure. Then I would be discussing the problem statement that you would encounter as part of this course. Okay, so what problem to solve, and then different solution methods that we could potentially employ to solve that problem statement. Okay, so let us get started.
In this very first lecture of structural dynamics, we are going to discuss about this course. What are the different concepts that we would be going through this course? What are the objective of this course? What is basically a simple difference between a dynamic system and a static system? And then I would be presenting you the problem statement for this course that we would be studying. Okay, so without getting much delay, let us go through this course. uh, if you remember from your undergraduate knowledge, you used to find out forces and deflection or different response quantities subject to a load, say P naught. Okay, so let us say a load P naught is being applied here on a beam of length L, and the modulus of flexure EI. Okay, now uh, remember, never at any point of time you were told how the load P naught is actually being applied. Okay, so it was just said that a static load of P naught is being applied on this beam, and then you needed to find out the response quantities such as forces and deflection. So my first question to you, can you tell me, if I have to ask you, how is this load P naught is actually applied? Or let us say in general, how a static load is applied. So what I mean to say, if you have to apply a static load of P naught on a structure, what would be the time variation of it? Okay, so that is my first question. My second question to you is, what is the deflection of this beam subject to this point load P naught? Okay, now you know it from your undergraduate studies that if the static load P naught is being applied, you calculated the deflection at the midpoint as the maximum deflection, and the value was P naught LQ by 48 EI. Now the question is, would this load, or would the deflection be always P naught LQ by 48 EI? Okay, so that is my second question. Okay, so what I am showing you here, the question is how the static load P naught is applied, and I am showing you four options. If you had to represent the time variation of this load P, for which the maximum value is P naught, how would you describe this static load? Okay, so I have shown you four options. Okay, so you need to select one of these options. If you would like, you can scan this barcode and open up a form which would show you all the options, and then you can select the correct answer, and then it would show you whether the selected answer is correct or not. Okay, so let us discuss these four options. So in the first option, I have load P naught, okay, which is being applied like this, a constant load P naught. But do you think it is physically possible to apply a load like that, like it suddenly goes to P naught? Okay, we'll discuss about that. In the second figure, you can see I have a maximum load of P naught, and then it decreases slightly so that it goes to a value of 0 over a certain duration. In third one, I have a load P naught, okay, which starts at certain time T1, it goes to P naught, it is maintained over a certain duration of time, then it again goes to 0. And in the third one, I have a load which is gradually being applied so that it reaches to a maximum value of P naught after a time duration. Let us say we'll call this TR, or the rise time. Okay, so which one do you think can be used to represent this static load that you have studied till now? Okay, now if you think about it, the only load that could be, or the load representation could be used, is actually this ramp load here, because if you try to apply this load or this load or this load here, you would see from the principle of dynamics that you would study later, they could never have an static load application through any of these representation. However, if you consider the fourth option here, depending upon the time value of TR, you might be able to apply a static load. Okay, and we'll come to that. What do you mean by static load and dynamic load? Okay, how do you characterize, actually mathematically, how do you characterize static load and dynamic load? Okay, so this was the first thing you heard about. You used to do analysis subject to certain kind of load. Let us say P naught is equal to 10 kilonewton or 20 kilonewton, and used to find out, like, the response. Okay, but now you need to understand how the load P naught is actually applied. Now let us come to our second question. Okay, so my second question is, out of these four options, or the four load representations that I've shown here, which one would give you a deflection that is most likely to be the value P naught L cube by 48 EI? Okay, so you have to select one of these options depending upon the plot of P versus T that is shown here. That would give you a value that is closest to P naught L cube by 48 EI. Now again, you can scan this barcode using your phone, either through an app or through your camera. Okay, and then you can submit the answer and see the correct answer right here. Now let us discuss each of these options that have been provided here. Okay, so the basic difference between these three plots A, B, C, what do you find the basic difference? It is basically the rise time that you see. So you can see TR is an intermediate. The first option has an intermediate rise time. The second option is the fastest rise, or I can say, like, the smallest rise time. Okay, and third is the largest rise time. Okay, so what I mean by this is that this load is being applied fastest, this slowest, and this is somewhere intermediate between these two. Okay, now I can simply discard this fourth option. Okay, because this would never produce a value of a deflection that is equal to P naught L cube by 48 EI. Okay, so my the competition is between these three options here. Sorry, go here. Okay, so what you would see, that out of these three, the loading that has the largest rise time would give you a load which is closest to being a static load, and we'll see why. We'll see, like, mathematically we'll also prove that. Okay, but physically you just need to, like, imagine that if you apply a load very slowly, then load is actually being applied statically and it does not produce any dynamic effect in the structure. Okay, so this one is most likely to give you the value which is P naught L cube by 48 EI. Okay, so Now let us come to what basically defines a dynamic system. Okay, so as we discussed, dynamic system deals with the variation of a state of a system or structure with time. Okay, of course, under application of external load. Okay, so I'll write under application of external force or load. Okay, so again I have shown you that representation, a load representation that can be used to represent a statically applied load of the magnitude P naught. Okay, now we saw that a parameter to determine whether a system would behave as a static system or a dynamic system under the action of external load is TR, right? We saw in the last slide, depending upon how fast you apply or how slow you apply, it might behave like a static system or dynamic system. Okay, to demonstrate that, I'll give you a simple example. Okay, so let me show you a spring, okay, which has a mass m and k, and another spring, okay, again same mass. So both of these have same system properties, but now I'm applying a load P, okay, of final magnitude P naught. Only thing in this one, TR or the rise time is much greater than TR in the second one. So in this one, load is being applied slowly, and in this one, load is being applied fast. Okay, now can you imagine, okay, forget about mathematical formulation, let us just talk about, like, have the feel of the system. Okay, first develop appreciation from the real life examples, then we'll get into mathematical formulation. So in this case, as you can see, if the system are same and I apply two load of final magnitude P naught, however, if one is applied slowly, what will happen? This spring won't vibrate as much as if you have a load that is being applied suddenly. So in the first case, load representation is something like this. In the second case, load representation is much more sudden. Okay, so I can say TR plays an important role in determining whether the system would behave as a static load or a dynamic load. Okay, now can you imagine some other parameter of the system that would determine whether the system is static or dynamic? For example, again consider a similar example, except in this case, let us say mass, let me keep the mass same, but I have K1 and K2, and in this case K1 is much smaller than K2. That means this is a flexible system and this is a comparatively rigid system. And now I apply a load which has the same rise time. So both load of final magnitude P naught applied over the same duration. Now can you imagine, if it's a flexible system, then it would vibrate more, and if it's a rigid system, it would vibrate less. Of course, I'm doing a relative comparison between these two. So compared to this system, I would see that load P, which is a ramp load, it would lead to more vibration in a flexible system compared to a rigid system. Okay, and I would come to technicality later, like, what do I mean by more vibration, less vibration, in terms of what response parameters. But in layman terms, just try to understand something like this, and you can appreciate this example from a real life, let us say a pedestrian bridges that you see. For example, like, the Jhula bridges that you see in some villages. It is also called a suspension bridge. So you have something like, let us say bridge which is very flexible and supported at the end, and then you have river going over like this. Okay, you can imagine you try to walk very carefully, very slowly here, because if you jump, it would start vibrating, because this is a flexible system, so the dynamic effect would be more. However, if you have a rigid system like a concrete slab bridge, okay, which is much more rigid than this, you don't need to be that careful as you would like in the case of a suspension bridge, or just a hanging bridge. Okay, so the second parameter that determines whether the system would behave statically or dynamically is the flexibility of the system, or more appropriately we would see later is the time period. So it is mass and k. So these two parameter, and if I represent time period as, this is actually what determines the second parameter. Okay, so depending upon the values of Tr and Tn, we can decide whether the system would behave as a static or dynamic under the action of an external load. Okay, so this thing you need to keep in mind. Okay, we'll come back to this later, and we'll try to do mathematical derivation of whether the system would act as a static or dynamic. Okay, all right. Now let us come to classification. So we saw that we have a ramp load here, right? Okay, and if we increase the value of Tr to very large value, then we can represent it as a basically a static load. Okay, now let us consider loads that you have been dealing till now, which were typically what? Dead load or live load. And a typical dead load included a simple load of, let us say, 10 kilonewton. Okay, and we said that is a static load. Now can you tell me why the dead load was considered as a static load? So dead load means what? Self weight of the structure or anything that is attached to the structure is considered as a dead load. And remember that dead load is not applied suddenly to the structures. If you are building a structure, you would do it over a day, or over days, over months, so slowly you are going to pour concrete and build the structure. Okay, so it is applied over day. And then you also have live load. Live load could be the habitant, or people that are going to occupy that building, or things that could be moved. Okay, so that would be considered as live load. Even that would be applied slowly. Okay, of course we are not considering live load analysis like a vehicle moving on a bridge or something like that. Okay, live load we are simply considering due to weight of people, or things that could be moved during the life of the structure. Okay, now so those are the typical static loads that you have encountered till now. Okay, now in terms of dynamic load, we can consider earthquake load, wind load, impact load, blast load, or tsunami load. And why do we consider these as dynamic load? If you consider an earthquake load, can you tell me what is a typical duration, or can you think what is the typical duration of an earthquake? Maybe let us say 15 second, 30 second, 1 minute, something like that. Okay, so structure is applied a very heavy horizontal, like a very large horizontal load over a very short duration. So this TR is very small. Okay, and depending upon the time period of the structure, it could lead to dynamic effect. Okay, and then I can also have wind effect, and depending upon at what rate the wind is flowing, or at what velocity the wind is flowing, I can have very large dynamic effects in the structure. I could have impact, which is like a sudden impulsive load, or I could also have blast, which is also like an impulsive load. And then I can also have tsunami load, which is a sustained load over a little bit larger duration of time than the impact and blast load. So these type of loads are characterized a dynamic load due to their duration over which they are applied to the structure. Okay, and the typical time period of the structure. Okay, so keep these things in mind. All right. Now what I'm going to do, I'm going to show you some videos of previous loads, or the real life example of different dynamic loads that we have mentioned in the last slide. First, I'm going to show you basically one of the few images of the Bhuj earthquake that happened in Gujarat, and you can see what kind of damage it resulted in. So all these buildings, most of these buildings were designed adequately, I can say, for vertical loads. They were designed for vertical loads, but I'm not sure whether they were designed appropriately or adequately for horizontal load. So earthquake is in horizontal load. Due to shaking of ground motion, it leads to horizontal load on the structure, and because of inadequate seismic design, it led to a lot of devastation during the earthquake and loss of precious lives. So this is the example of what dynamic load like an earthquake can do to the structure. Then here is a video of Nepal earthquake. You can see this is a live CCTV video at that time, and it is showing you can, I'll just show you a small clip. You can always go to YouTube and see in detail that all the clips you can see. Let me run this video so that you can see it here. So you can see the shaking happening, and soon you will see the intensity increasing and a lot of structure. So you can see that there is a structure that just fell. Okay, and there are 10 different footages at different places. So so you can see another footage is here. I think the structure already collapsed. Yeah. So you can see the effect of earthquake on this residential house as well. A lot of pots falling around, and people coming outside. Okay, so you can go and search on YouTube's different type of earthquake loading and the failures on the structures, and you can see what is the effect on different structures around the world for during different earthquake. Okay, now the second type of dynamic load that we discussed was wind loads. What I'm going to show you, this is a suspension bridge known as Tacoma Narrows Bridge. You can see that one morning, due to wind effect, what is happening is actually what happened. A lot of wind started flowing below the deck, and due to pressure differential, it started creating torsional motion of this deck. Okay, and which finally led to failure of the suspension bridge, precisely the deck of the structure. Okay, so let me just play this video. Of course, there are a lot of failure studies which would more accurately describe the failure mechanism and what led to this failure. You can go ahead and look, if you are more interested, go ahead and look into those studies. Okay. So you can see this deck of the central span wobbling vigorously, and the amplitude keeps on increasing. So I'm going to fast forward this video so that I can show you the final failure video of this one. Okay. Oh, let me again go here. This is showing the front view of actually the funny thing happened. One of the dog was actually left in the car, and then the owner of the dog actually went ahead and then actually rescued on this wobbly deck. You can see that the amplitude is increasing. I'm again going to fast forward this video so that so we also have a suspension bridge, right? We have a suspension bridge in Bandra Worli Sea Link. If you've not gone there, it's a great engineering structure. You can always go there just to have a look and look carefully at the suspension bridge that we have there. So you can see that due to increased basically deflection because of the wind load, it finally led to the failure of the deck span. Okay, so and now, like, all these type of structure need to be designed against such wind load, so that even if there's a constant energy infusion due to wind, then there should be some energy dissipation mechanism, and about which we'll learn later, so that it minimizes, or it actually, like, trunk, or basically it keeps the amplitude within a certain limit even if there's a constant fusion of energy. Okay, now let us go to the next video. Not yeah This is a crash test video. So the third type of dynamic load that we talked about is the impact load, which is a short duration pulse. Okay, so this is one of the tests that was conducted. Now if you, because of the security threat, many of the structure now need to be designed against aircraft impact, and this was one of the experimental tests done, in which a concrete wall actually was hit with the Phantom F4 aircraft, and then it was seen whether the aircraft would be able to take that load or not. Okay, so let me just play this video. So what do you think, whether this aircraft, whether did it breach the wall or not? Well, it just so happens, even the load was very high, the wall was designed in such a way that there was a lot of damage due to this impact. However, there was not a complete breach, and that is what these walls actually designed for. Heavily reinforced concrete walls are designed for. Okay, all right, so I'm going to go to the next slide. Next type of blast impact, dynamic load is a blast load. What I'm showing you, a building before and after bombing. This is a building called Federal Building, Alfred P. Murrah Building in Oklahoma City, and it was bombed in 1995 using explosive kept in a van. The explosive weights were 1800 kg. What it did, actually, it due to the blast, it took out the columns here, columns and beam here, and it led to, so first it led to the removal of columns here, and then because of the blast pressure shock wave, there was an upward pressure on these slabs which they were not designed for. Okay, so due to this, it led to the progressive collapse of the building, and finally what you see here is the building partially collapsed. So I think a lot of fatalities happened, around, sort of total number goes around 160 people died in this building. So now many of the buildings are whether there are critical, like, civil building. Civil building means, like, for civil purposes, non-military purposes, they are now being designed. Aircraft buildings are being designed. Some operation control centers are being designed for blast loads, and also military structure, defense structure have always been designed for these type of loads. Okay, next is a very simple, but demonstrate the concept of dynamics. It's a vibration due to walking. I don't know how many of you have taken a course in have you taken, like, as in your curriculum you did NCC as part of your curriculum, or either, I don't know whether you know about somebody would have told you that when you walk on a bridge, whether it is a pedestrian bridge or regular bridge, you should not walk in tandem. And even, like, forces, military, or the these they are supposed to walk in a tandem, in a periodic fashion, in a normal situation. However, they are advised against walking like that on a bridge, because what happens when you walk in a tandem, you create a walking load frequency. We'll see how does that look like, walking load. Okay, and that leads to basically a walking load with a certain frequency. If the frequency of that walking load matches with the frequency of the structure on which you are walking, it leads to the failure of building. Okay, so they are requested to break their steps. Breaking their steps means walking randomly. So there are multiple frequencies with very small amplitude. Okay, but not a single frequency periodic load with a large amplitude. Okay, all right, so let us go to the pretext of this course. Okay, so what you see here, what is the problem statement, okay, for this course, or what we are trying to do here? Okay, so the problem statement is, how to build a structure that can sustain those dynamic loads that we have discussed in previous slides and mitigate their detrimental effect. Okay, so that is a larger goal. Okay, and what is the solution for that? Well, the solution for that is to design structure for dynamic effects of load. Okay, very simple, right? But it is not as simple as this statement make it sound. Okay, so what is required to do that? Well, first I'm showing you a structure here. This is a you can think of building a structure here. To obtain and design a structure, first what you need to do, create a numerical model of this structure. Okay, because you cannot have a numerical model that includes each and every minute detail of any system or a structure. Okay, so you need to create a simplified representation which might be single degree of freedom system, or if you need, depending upon what is your response quantity of interest, you might create a multiple degree of freedom system. Okay, what is the next step then? Well, once you create a simplified model, you need to find out what are the stiffness, what are the damping properties, and then from that, what are the time period of the structure, what is the damping is basically represented, let us say representing it by viscous damping, so you need to find that out. Okay, and then you need to find out the dynamic loads that are being applied. So in this case, let us say I have an earthquake here, okay, horizontal earthquake. So I will represent it through some time history function. Okay, and then I have a numerical model and these time history function. The next step is to find out the dynamic response of this structure. So response means what are the forces, the base shear, let us say, what are the moments in the members, okay, what are the displacement here. Those are the typical response quantities. Once we have that, I can design my individual component or overall structure to accommodate those kind of forces and deflections. Okay, and the final step once I have that is, as I said, to design the structure to minimize and sustain those dynamic load effects. Okay, now first three steps are analysis steps. Okay, and the fourth step is basically a design step. Now the scope of this course is to study first three analysis steps. So we are not going to go ahead and go design structure, but definitely we are going to study first three steps. So through this structural dynamics course, we are going to analyze system and find out the response. Okay, there are other courses that are there and which we will see subsequently that will discuss how to design the structure once you have the effects of dynamic loads figured out. Clear? Okay, so that brings us to the context. Okay, so the context is, where does this course, whenever you start a course, for the first question you should ask why I'm studying this course. Okay, what I'm going to achieve through this course. Okay, and how does it fit into a bigger picture. Okay, so let us say if your goal is to become a structural designer or analyst or computational mechanist, so you have to first find out what is the utility of those course and how it's going to be useful and how does it fit into the bigger picture. Now let me draw out the whole curriculum and then show you how does this whole thing actually builds up to work towards a greater goal, to equip you with the skills that are required to work towards designing a structure, analyzing a structure, okay, and finding out or basically building safe and economic structure. Okay, now in your undergraduate you would have studied a lot of subjects. Now let us see where those subjects actually fits into this picture. Okay, so what are the steps required to design a structure as we discussed before? Well, the first step, you need to find out forces on the structure, right? And which course did you study to find out forces on the structure? Well, it was the first course was engineering mechanics, right? Now forces might not be enough, right? Because most of the times failure criteria are governed by the stresses, not the forces. Okay, so to get the internal stresses and strains, you studied solid mechanics. Okay. Now, after you studied how to get the stresses and strain, you also needed to find out how to get internal forces and displacements in a structure. And what did you study for that? Basically, a structure analysis course. Okay. And finally, when you were equipped with all the analysis courses, then you studied specific courses that were for the design of different type of structure. So whether it was a steel design course and concrete design course. Okay, so these were at very preliminary level, very basic level. Now at the advanced level in the graduate curriculum, let us see what are the courses and how does this course fit into the bigger picture. So now what are the steps required now for advanced analysis and design? Okay, so you did basic analysis and design in your undergraduate. Let us see how do we do, what are the steps required for advanced analysis and design. So to find out the same, the forces on a structure, now you do advanced structural mechanics, which discuss advanced methods of analysis. Okay, and then you also now study a course which is called advanced solid mechanics to find out stresses and strains. In your undergraduate you mostly focused on linear stress and strains. However, in a graduate you might do linear and non-linear both. Okay, and then to obtain forces or stresses and strain, you need some knowledge of numerical methods. Okay, and to learn those numerical methods, you take or you are going to take a course which is called numerical methods. Okay, which is part of a curriculum that our department also has. Okay, and then till now, whether it is undergraduate curriculum or graduate curriculum, these courses were focused on static. Again, these courses are focused on static. I mean, you can do dynamic advanced courses, but the first course that you have which deals with the dynamic effect of loads on a structure is this course, structural dynamics, because most of the loads are actually not static, they are dynamic. Even when you call a load as a static, they are still a dynamic load which has a variation with respect to time but applied very slowly. Okay, so I hope the context of this course is clear to you. Okay, so again let me come to the problem statement. So what through this course we would be doing, first we need to find out what is the load that is being applied on a structure. Okay, so first we need to determine the load history. Okay, the second step is develop mathematical model of a structure. So whether it is a building or whether it is a vehicle or whether it is any other type of system, I first need to represent that system or a structure through numerical model or a mathematical model. Okay, once I have that with this loading history and the mathematical model of the structure, I would set up what is called equation of motion. So I would formulate this equation of motion and we would see how to do that for different type of system, and you can extend that to a very simplified as well as complicated systems as well. So I need to first set up this equation of motion and then solve this equation of motion. All right. Okay. Now after this, once I have the equation of motion set up, I would find out the response quantities. Okay, so obtain numerical response. And what are the typical response quantities I'm interested in? They could be this could be displacement, velocity, acceleration, and force. Okay, so these are the response quantities I need to find out. So this is basically the problem statement, and basically through different chapters of this course we are going to addressing one or multiple steps at a time. Okay, so keep this problem statement in mind, okay, when we will go through different chapters. All right, now let us look at how do we obtain this load history. What I'm going to do, I'm going to present in front of you typical load history that a structure or a system might encounter in real life. So the first one is a harmonic loading, which might be a sinusoidal or cosine loading. This type of loading you can imagine due to some machines or vibration happening due to machine attached to a floor, or like other type of harmonic so basically machines producing harmonic motions. Okay, the second could be periodic loading. Now periodic loading might not be harmonic, but harmonic loading is a periodic loading, so just keep that distinction in mind. So periodic loading is something that repeats after a period, which is T naught here. Okay, so what I have shown here is basically this is like a representation of a walking load. Okay, of course this assume a uniform walking at like at a fixed pace. Okay, but this basically represents a walking load. Okay, then there could be earthquake load, which is more like a random excitation. Okay, there could be a wind load, which again could be represented by these random spikes, which represent the pressure peaks. Okay, there could be impact load, which is like a sudden spurt of a load, okay, for a very small duration of time. And there could be a blast load, which is like a sudden spike and then decreased, and this duration is actually very small. Okay, so I've shown you some of the load history that a structure might experience. These are the load history and typical load scenarios that would experience in while obtaining dynamic response of a structure. Okay, so once you have the load history, second thing we talked about is mathematical model of the structure. And pardon me for the mistake here. So in mathematical model of the structure, I can represent my structure using a single degree of freedom system, and I'll tell you like what does that mean, the degree of freedom, in a later slide. Let us say I have this pergola type of structure where this is like a walkway in which a heavy slab is actually connected or supported through these steel columns. Okay, or you have a water tank in which again a heavy mass is connected through this column. So this can be simplified through a single mass and then a single stiffness component represented by this column, and this is called single degree of freedom system. Or we could encounter like more complicated system in which I have a very complicated structure and I might decide to simplify at simple beam columns and then applied by loads here. So the slab loads and everything can be applied here. Okay, and then horizontal load might be applied here or a vertical load might be applied here, it depends. Okay, now this structure can be further simplified if we assume that the all mass of these floors are rigidly connected to each other and the flexibility is basically represented by these columns. So I can further simplify this system through this 3 degree of freedom system. Okay, now you would ask which is the appropriate representation. Well, it depends on your problem and it depends what are you trying to achieve through that problem. Okay, so for some system even this could be represented by a single degree of freedom system. Okay, if let us say your goal is to find out what is the total base shear and not what is happening in the structure above. Okay, or if your goal is to find out what are the story shears, okay, then you need to represent it through a shear type building or building like this. Okay, so it depends on what are you trying to find through that problem. Okay, so coming to what are the different components of a dynamic system, you have to think about what happens when a force is applied to a deformable body. Forget about this slide, don't look at this slide right now, but just think you have a deformable body and then you apply a force that is varying with time. Okay, so can I say if you apply a force on a deformable body, then there would be an acceleration. So motion or acceleration, let us say motion or acceleration. And if it's deformable, then of course there would be deformation. And can you imagine if I apply a load to a structure, there would be some sort of energy dissipation. So in reality, every system, every structure in reality would dissipate some amount of energy when you apply a load. It might be small, so in some cases it might be neglected, but for all practical purposes there is always some energy dissipation. Okay, so the third component is energy dissipation. Okay, so considering these points in mind, any structure or a dynamic system has 3 integral properties, which are mass, which is basically ability to resist acceleration. Okay, then stiffness, which is ability to resist deformation, and then damping, which is the ability to dissipate energy. Okay, so a simplest representation of a dynamic system is a spring mass damper system. Okay, and this is called a spring mass damper representation. And if this spring mass damper system is acted upon by an external force Ft, there would be a response, which is here displacement. Okay, so I can say the dynamic behavior of any system can be studied by modeling it as a combination of spring mass damper system. Okay, so although I have shown you here a single spring mass damper system, let us say even if I have interconnected body, I can lump the masses. Okay, I can lump the masses, connect them with a spring and a damper like this. Okay, connect them by spring and damper. Okay, and each of them can be connected through each other node. Okay, depending upon what is the connectivity. Okay, and through this any system can be represented by a spring mass damper. Okay, so what I need you to do basically when you are doing this course, try visualizing every system what you see around yourself as a representation of a spring mass damper. Okay, and of course if you can tell me that to solve this system I need to represent it with some additional properties, then let me know, because this I find is the most simplest representation of a dynamic system. Okay, so what I want you to do, ask yourself few questions at this point in time. Okay, in this introduction slide, how the car shock absorption works. Okay, so you have cars or any other vehicle. Okay, and our Mumbai, especially Mumbai is famous for potholes, or our Indian roads are famous for potholes, and all the cars or any type of vehicles are actually equipped with shock absorption. So you need to imagine how would that actually work, and if somebody has to design that car shock absorption, how would they do it? What would be the critical parameter? Okay, then what I want you to ask yourself, you guys have traveled by train and you must have seen, or the metro, you must have seen there are blast or crushed stones below the rails. Okay, what is the function of that one? Why can't I just have rails on the top of, let us say, concrete slab? Okay, and then just run vehicle on the top of that. So what is the utility of that? Okay, and then you might have also traveled by aeroplane. Have you ever noticed which wheel the aeroplane any aeroplane lands on, whether it is front wheel or the rear wheels? So just try to notice that next time and try to find out the reason why the rear wheel or why the front wheel. Okay, and then I need you to ask yourself, what will happen if a very fast moving load hits a very stiff structure? Okay, or a very fast load hits a very flexible structure. Okay, these two questions I need to. So these questions I want you to leave. I want you to leave with these questions. Okay, keep pondering about these questions, because the answers to all these questions would lie or would be answered in future chapters that we study. Okay, so and these questions are just example. Always try to imagine whenever you see the systems around you, try to visualize why what is happening and what is the mechanism behind that. How can I explain that? There are so many examples of dynamics around you, or the structural dynamics around you, that it would become very interesting when you start looking and analyzing those systems in your mind. Okay, so with this question I would leave you. We'll come back to again these questions in subsequent chapter, and we'll see, I'll explain the basic concepts behind those principles, as well as the mathematical derivations of these principle or the questions and answer to these questions. Okay, so thank you for your attention, and let me just leave you with these questions, and we'll come back to again in next chapter. Okay, thank you.